Okay, great.
You're always recorded. You just don't even know it.
Okay, so I'm not sure if anybody here has experience with hardware. Like, just actually gotta get it. Where is like? Oh, I can't actually see my camera now. That's great. I was gonna say, show of hands. Yeah, how many people have experience with hardware? There's only three of you in there. The hardware is one of those things where it's like if you've done hardware, if you've done software enough, you kind of like you get into hardware and you think this should be easier. Like, why are we still stuck in the 90s? And so I started my career in hardware, basically like learning aircraft electronics. And so it never seemed difficult to do electronics until you see like doing electronic PCB design, all that kind of stuff. It's all Windows based. There was no Linux support. And then you get into software and you kind of like get exposed to how nice things can be. And so I've become like unwilling to put up with Windows and just bad UI design. So basically, that's what led me down this path. The only reason I still have a Windows machine is to use tools like this. So this is like the last barrier before I can just like uninstall Windows for good. And I think this might have this might be the last thing I need on Windows because apparently Linux gaming is a thing now. So this is gonna help me make the move. All right. So the idea is I've done Raspberry Pi programming, things like that. Like you can do some low-level ARM programming, or most of the time when people say embedded development at this point, they mean embedded Linux. So if any of you have tried like Nerves, Nerves is cool. Like running Elixir on a microcontrollers, or I say microcontroller, not really a microcontroller. It is a little mini PC. They're running Linux, right? They need a decent amount of RAM, a decent CPU. They're not real time, especially if you're running Linux or if you're running Erlang. And so this gets like a level below that. Like when you get down to like real microcontrollers, like an ESP32 or an STM32, you're effectively like the highest level you can usually get is something like C. There are some ways to get Python and stuff to work, but you're giving up a lot of performance that way. If you go a step below that, you can get to essentially you're programming the transistor layout. You're programming what's called LUTs, which is the lookup tables for the logic cells. I didn't get time to set up. I had a really good idea for a good demo that I didn't get time to set up, and maybe we can kind of half program it later. The FPGAs are essentially you can think of it like you have inputs to a logic gate, and if you think about defining a logic gate, whether it's being like and, or, nor, not, if you thought about like we have this table of possible gates we could be, all I can get if I just give you like 4 bits, you can essentially configure this thing to be any one of those possible gates. And essentially, that's what you're doing with FPGAs is you're putting a bit in one of 4 places on a lookup table. And there's like in this case of some of these ones, I have 100,000. Let's see, the highest one I have. No, sorry, I have a 20,000 one here. So 20,000 lookup tables, all with 4 bits apiece. So that's what you're effectively doing. So the key thing to remember is they're not CPUs. You're not programming them. Actually, people get really offended if you say programming an FPGA. They'll like correct you and say you're I don't know. There's some other word they have. It's hard. It's a hardware language. It's not a programming language. Um, so the hardest part is getting out of the mindset that things are essentially sequential. That as you're reading a file from the top down, it's like this happens, then this happens, then this happens. Um, I mean, I'm sure most people are thinking like, why would you use Elixir for something like this? It does seems like Elixir, like it's not suited for this. It's not the most performant language. It's clearly it's a functional language, it's a very high level language. Like why even use it? And what it turned out was that Elixir's macro system was super convenient to do some of the things that you'll see later. So that was mainly this is just me using Elixir for things that probably shouldn't be used for. So when you get to the end of this, don't come away thinking, wow, that's great. I'm going to use this for like production systems and mission critical stuff because it's most likely not a great idea, but that's generally where the most fun stuff is. I'm not going to go through every single thing in here because I'd rather get to the point where we can see it in action. But if you're used to Elixir, which most of you are, right? The idea is I wanted this to I want it to look as much like Elixir as possible. It does use a ton of macros, so it's going to look a little different. But at the top of what I call a module, which a little bit of a weird overload of terms here, but that's what they call in hardware terms. We use this hardwire module, and that pulls in some these macros we're going to use. And this goes into really detailed, like under the hood, how that actually works. But you can think of it a lot like how Ecto or Inex works. Under the hood, it's keeping like these module attributes that it's like appending things to, and at the last second, like reverses them to like get out a list of the essentially the AST for what this hardware should look like. And the goal, like I like to think about things from a user experience level down. And so what I really, really wanted was to be able to drive most of the stuff with mix with really simple CLI commands. So you don't really have to deal with like external tooling. It's not like saying go use Yosis for this and next PNR for that, and go like run this command. Like everything should be driven with standard Elixir tooling, because that's where Elixir shines. That's one of the reasons I wanted to use it, was we have great dependency management, great macros, and great tooling. So let me see. I think this one down here, yeah. See what's actually happening. And actually, I'm gonna. This intro got a little long. I'd rather look at the code before we. If I show you the code first, then we can look at. Here we go. I want to give a quick reference of like what kind of code I'm talking about here. This is system Verilog. This is the language I tend to use, is the more modern one. There's modern language. There's one called Verilog that this kind of added to. You can think of this as the C++ to C being Verilog. And there's also a couple other languages that are used in like very specific locations. Aerospace will use one, like federal stuff will use another. Like in Europe, there's really popular is like VHDL. But they all kind of look like this. They all have a similar kind of layout. And if you kind of squint, they almost look like maybe Python or something, right? They clearly, like, there's what looks like kind of function input here. And then there's some assignment going on. This I'll get to later. This always FF. I mean, if any of you could decipher what this means without having any experience, like, good luck. Like, this does not, none of this reads well. There's also this, you can see this arrow syntax. Like, clearly it's some kind of like assignment, but it's like, well, what does that mean? And then there's a bunch of nested if-elses, right? But if we kind of look at what this is saying, I'll give it a little bit of an example. Pos edge is positive edge. Oh, great. I can't double click on things or it will. Positive edge is the positive edge of this clock, or the positive edge of the reset button, right? So you have some signals coming in, one of them being a clock, one of them being a reset. And so this is like, okay, well, kind of looks like when this event happens, I'll like fire this stuff off in here. So with just a tiny bit of programming knowledge, you can kind of see what's going on here. But if you turn this into Elixir, one, we can choose better names like combinational, sequential. So what we're saying is there's a block here that is, I'll get into what that means, combinational, and a block here that's sequential. You see here it has the clock, the combinational doesn't. This is driven off of clock, right, or reset. So both of these things. I left off the whole positive edge, negative edge, both part here, but you could, because the default is positive edge, you don't have to even define it. And then again, you could see inside it's saying like if we're enabled, so this EN is enabled. If this OVF is high, if the OVF output that was here is high, then set the count back to 0. If not, increment the count. So you see all this is doing is essentially just counting while it's enabled. And while whatever this OVF isn't high. And then, so this is pretty clear to understand. There's a clock pulse coming in, ticking, some counting is happening. This one is a little weird, but what this is saying is not on a clock pulse, just essentially you can think of it as, it's just a stated fact, it's forever. OVF, as long as the count is equal to 255, OVF will be 1. If the count is anything else, it will be 0. And this happens, you can kind of think of it almost like a computed property maybe in JavaScript or in like a Ember or React or something like that. You're essentially saying like there's some property on this that we're changing, and like we're changing count, and this is just watching it, whatever count is, we're just setting this OVF pin. Functionally, they're very different. Like the sequential one, the sequential blocks literally have a clock. Like they're built with flip-flops that have a clock and they're actually gated. The combinational one, this is the one that I really wanted to get an example of, effectively is instant. So if you have a board that has like 5 switches and you hooked all the switches up to a light and you're like pressing them and you make them like AND gates or something, they're just instantly firing off. There's no clocking going on. It's just whatever the input is, the output turns into. So it's like pure logic gates. And you need both. You need
flip-flops?
What was that?
Did you say they're built with flip-flops?
Yes. Yeah. So you have flip-flops are what are running the sequential part. And you can think of I don't think I have a great diagram in here for what a flip-flop is, but essentially you have some gated input, and then based off of like, so while this clock pulse is high, you can set this thing. And so if you set the an input pin while the clock is high, it will remember. And so if you don't set anything after that, as long as the clock will be ticking, but the output will just remain the same. It's like the simplest form of memory, but it's a clocked memory. The clock has to be high in order for it to be set. But under the hood, a lot of you don't really deal at the flip-flop level, and you can write system Verilog and all those at a gate level. You could literally use straight like AND gates, OR gates, and all that. But where the stuff gets really powerful is this high level synthesis where you're writing the intent of what should be happening, which is like that the count gets incremented, not like this AND gate does this and this OR gate does that, or this flip-flop does this. So you really don't want to be writing at that level, but under the hood, that's what these are all doing, is creating a series of lookup tables and flip-flops, like configuring them. And let's see. So this was what I thought was really interesting when I started working on this. I started working on this years ago, and me and Micah took a little class. I think while we were at Heroku, they like did this thing one week or something where you could like essentially take the week off and do a class or something. And we did this thing called NAND to Tetris, where you I don't remember exactly how it was working, but we were creating logic gates and then essentially building up a little virtual machine that would eventually, or a little architecture that eventually you could actually write a game that was somewhat like Tetris. It was very, very basic. That class has actually been extended to be NAND to Mario, so they build a much more complicated game now. Like during that time, like right after we did that class, I was like, oh, I want to do, like I'd already used FPGAs a little bit, but I had this idea that I wanted to write this Elixir-based HDL, which is hardware definition language, to do what we were doing, so that we didn't have to write this like Verilog that we were writing. And I got a little bit like into it and quickly kind of hit a wall because my experience with Elixir and my amount of free time. Now I have much more experience, and Claude has a lot of free time for me. So I basically just said, like, here's what I'm thinking, here's what I wanted to do, how possible is this? And Claude just turned away and made it work, which was amazing. And there was things that I didn't even think of that even with some experience, I didn't know all of the things that these other languages that have come out since then were doing, and things that Elixir could do better. So one of the things that's really, really great is implicit widths. So a lot of these other languages, which we'll go into, that do something similar to this, where they're like transpiled into some lower level HDL, they have to manually specify a lot of information, and it mostly boils down to they either don't have a macro system at all, and so they have to be very explicit because they're making like Scala data structures, or their macro system is just weak and they can't be powerful enough, right? Or some of them, I'm sure some of them just took a different step and they don't like the magic. But in my case, it was really nice to be able to say, this output, I just pass into something else, and I don't have to say the width of it. It can kind of infer, because there's some metadata about when it was created, it can infer the width of that line. Meaning that, it might say output, but that output is 8 bits, meaning there's 8 actual wires as part of the output. Let's see, what is the rest of the... Yeah, and then the tool chain was also something that, like, I'm not going to go into examples of how these other things work, but like when the first step is install Scala, it's like, or install Java, I'm like, no, okay, never mind, I'm out. So Elixir was a great choice. I think I basically covered most of this, but what I did want to cover was the few languages that I was talking about as examples, which are Chisel, which is probably the most popular one. Most of these are academic, or at least started academic, but they've grown really large. Like Chisel is written in Scala, and it was used by a Google team to write the hardware definition language for one of their tensor processors. Not all of them, right? Like Google's, if you watch the video of the people who did this, this isn't like everybody at Google uses this. Their team used it, but they had to heavily modify it. Like right as they were about to start using it, it updated to version 3 and broke some of the stuff that they wanted. So they basically had to like pull all these 2.0 features into it to preserve this backward compatibility they wanted. So they did heavy modifications on it. But what they did was a lot of these HDL languages, you start by saying, I want to program them, try them out, kind of iron out all the kinks in the API essentially of this chip, and then I'm going to bake them into a real ASIC. I'm going to like send them off and have them actually fabbed somewhere. So the same language can be used to like test out the chip, and then also like sent over and like baked into a real, which they eventually did with their. These were like edge devices like years ago. Like it was like 5 years ago when they were doing inference chips with like with Scala and Chisel. So that was kind of interesting. Clash, yeah, there's one in Haskell. Amaranth is the other popular one that was around the time I first started looking, which is Python. And then, yeah, then the best one, which is the one in Elixir that is super beta. So as an example, first, let me walk through this. Since we already looked at the other one, we're gonna, this one looks like actually a little simpler, which is there's a sequential block that's on a counter or on a clock, and then there's a combinatorial or combinational that is, this part's going to look a little weird, but if you look at what it's doing, it's saying go into the 23rd element in this counter, which is 24 wide. So also this also shows what I was talking about, where I'm defining it here with the width, but then nowhere else do I have to actually say, like when I say +1, it just like knows what that means. I didn't have to say like add 1 and the width is this high or whatever. And I didn't have to make this 1 be like a 24-bit wide number manually. It just kind of automatically happens. Anyway, so what this one's doing is, if you think about, you have a 24-bit number, and this thing is adding to it at whatever the clock rate is of this, FPGA. One of these ones that we're going to do is like 27 megahertz. So think about how fast this number is ticking. But then think about how many possible numbers there are in 24. And so essentially, if you were to watch a binary number, it counted up to as fast as it possibly can at 27 megahertz. The low numbers are going to tick real fast, and then these high numbers, the higher up you get, the slower they tick. So this is like a poor man's way to blink at a slower rate. So if you lowered this to 22, then you're going to blink. Let me see if I get this right. I think you're going to blink slower because it's actually reversed. So we can try this out and make sure I'm right. But basically, if you change the index, you're going to either half the time you're blinking or double the time it takes for you to blink. So let me see if I can get something set up where we can easily do this and also see it. Which one? This one. And actually, so if we have this blinky example, so this is a great time to actually just look over use the actual tool chain. Get to that one in a second. It's on 2. I need to move this to. How do I move this? It won't let me. Well, that's going to be interesting. I'll just open a different window then. And what's your window anyway? Oh, that's the video too. All right. All right. So the there's actually I'll mention this. I've broken this whole thing up into a few different modules. We're going to start with Hardwire. That's like the basic stuff. Cores we'll get into. That's like when you build a kind of reusable thing. You think of almost like a component. People call it cores. a lot of people call them IP, like intellectual property, and I hate that. I just hate that name. It like implies like, I'm just gonna nothing's open source, which mostly it isn't in this world. And then we'll go into these other examples later. Yeah, see, I thought it was there. It literally won't let me alt tab in here. There you go. Do it this way. You guys will go over there. Okay. Zoom sharing link is going to be in my way every single time.
How many editors would you say you have open currently?
Oh God, let me say, like, there's an editor in every tab, and there's 3 in this one.
Yeah.
Yeah. Oh, and I don't even have them all. I mean, I don't think I have any quads working right now, but yeah, usually it's churning away. All right, so first thing I'm gonna do. Okay, this is gonna be really annoying. If anybody leaves a comment, it apparently pulls me back to the window. So yeah, that's gonna be really really bad. Okay, so hopefully I still have some memory. So if I do mix build this one right here. So examples Blinky. So let me know. You probably none of you can probably see this, and it will not let me make it bigger either. Windows, really? Or Windows, Linux. Wow, I literally can't. I can't make it any bigger. Sorry. So what this is doing is right. It's calling the HDL build. I have this. This thing will take one of any of my examples that are in this directory examples, and then the thing you have to pass to it for it to know how to synthesize this output is the board, which has a bunch of definitions. We'll look at that in a second. But it basically says, here's all the pins that I have available, which are kind of broken down into resources and connectors. Different libraries do things differently. I like to break them up by like actual purpose and then like underlying connectors for like just general I/O. And then this port map here is like if you look at this Blinky example, which is this one, like we have a couple of inputs like clock and LED, right? So I need to tell this thing that I want you to hook this clock up to my board's sys clock, and I want you to hook this LED up to my board's LED 0. So that's essentially what is happening here. So if we hit enter, you'll see it's going to go through. So most things take forever to build. I love these little small ones. It builds this output called FS here. And if you open that, it's going to look like just a bunch of ones and zeros. It's funny that it literally codes it as ones and zeros as text because it means it's like 8 times larger than it actually should be, and more than that because it has new lines. But for whatever reason, this is the output that they choose to make with this. The tool that does this, by the way, there's a couple tools in line here. We'll go into them more in the docs. But there's Yosis, which turns like the system Verilog into like essentially a JSON file of like, hey, this board has all these features, and here's like what we need to make. Here's all the resources I actually need. I need this thing to be a lookup table that's like, 5,000 of these, and this connected to this connected to that. And then there's a place and route, which is basically like it has to now say you said you needed all these things, and now I need to actually like put that on the device and literally find like what specific orientation will let me like maximize the usage of this, fit everything you want, and then also meet critical timing. So you'll see that in this case, they're saying, with this really simple design, you could support a clock rate up to 444, megahertz, right? And it ran a couple trials and said you only wanted 27 megahertz. This is the crystal that you have. So this is way meeting it. You're totally fine. You can burn this. You'll see in a later example, I bump right up against this, and then sometimes it won't actually meet it. So that's like there's 2 different constraints you're looking at. You're looking at the number of lookup tables and just general like, the count that are on the chip. But you're also looking at like depending on how complicated your setup is, it might take 30 minutes to build now because it's basically having to like try all of these different options to fit it on the chip. And then to program it, I made it pretty simple. So it's the same Oh, I gotta do it. Why do I have it that way? Will that work? Yeah. Should be FS. I don't know why this one is even in there like that. There's two different programs I have to use. One's called Open FPGA Loader. Shut up. USB on these things is a little finicky sometimes. If it doesn't show up with a pop-up, it means that it like the ports sometimes get essentially corrupted, and then they just don't want to work. I think I'm just actually using too much power out of the USB ports right now. I'm gonna do. Oh, that's gonna be really annoying. I'd have to like program it and then plug back in the camera. There we go. Okay, so now we go back to this camera here. It's great that the cameras can be so far behind because you're not going to see the actual blinking's happening. But you see this blink right here. It's blinking much faster than that, but for whatever reason, I guess because of Zoom. Actually, let me stop this. Can I stop the screen share and just do that? No, probably not. Don't know if there's any way to make this camera actually go faster. Try it this way. $240. Yeah, you can kind of see it a little bit, but right. Anyway, so this LED, right? There's 6 LEDs here. You can barely see them because, of course, this camera will not focus or anything. And anyway, so that's LED 1, right? So to prove that this is actually working, we'll go here and we'll just change this. There's a couple things I'll do. What else we do? We can change the pin we're mapping it to. So instead of LED 0, we'll do LED 5, which means it will basically be the one all the way to the left on the screen. And then also we should we make it blink? It's like much slower. So we have 24 pins. This is like the highest one, which is going to blink the slowest. But if I pull it down to like 10, or actually no, 10 is going to be way, way too fast. Like 16. And then I'll program it. Yeah, so it's still way too fast. So you can see the light, it's got to catch up. Yeah, the light is just, even for me, is just on. Like that's just way too fast, right? It's blinking way too fast. So anyway, the lower you go here, you can imagine you have like, 1, 2, 3, 4, 5. Right, so you have all these all these zeros. And before we were saying when this one rolls over, the one on the left, we'll blink it. And now, we're kind of saying right in the middle or something, we'll blink it. So okay, yeah, one more time, I'll program that. It should be at least visible, yeah. So now it's like visibly blinking, but it's like a strobe light. So on the camera, it'll probably look all like just half dim. Yeah, there. Oh, yeah, this is really going to make all the rest of the demos terrible unless I can just hold it up to the camera. Actually, let me do that. So does this actually look, can you actually see this? Like see my camera?
You're not see ourselves.
Oh.
Let me see.
Can you stop sharing for just a second, Chase, so that we can, because it's like the whole screen is, there we go. There we go. All right.
Can I see you? God dang.
Can you see
So
us?
can you see that? Actually, can you see my webcam though? I don't know why it's not showing me though.
Opinion.
It's blinking so fast though that like it looks
Still looks
steady.
solid.
Yeah. It's blinking super fast. It's so weird that I can't see my own gallery. There we go. Now I can see it. Okay, so what is that? Yeah. To me, it's like blinking super fast. All right, good to know. All right. So now if we go back to share. And It's amazing this is possible on Linux, because before I would have never tried to do a screen share on Linux, but man, it's not perfect. Oh, you know what would make it a lot better though? Is to plug in my laptop and not be sitting here dying. Probably why it's going real slow. It's thermal throttling or something. Or I mean, battery throttling. All right. I mean, I had it in performance mode, but I'm not sure if it was actually going to use that when it was on battery and that low. All right. You go back to this dock. Through the blinky, right? So yeah, we already went through this, but actually, I do want to cover this, right? So clearly, like this is the magic here, right? Use hardware module gives you the access to all of these macros, and we'll get into also later, like what is this squiggly, and why is this having to be put in parentheses and all that kind of stuff. But essentially, the macros you can see are input, output. We have this signal line, like this one, yeah, signal here. Signals are like, you can think of a signal as like an internal thing, right? We're not outputting this anywhere. We're not getting it from an input. So it's just something, it's the same kind of wire. It's just internal to the design. Also, I'm pretty sure that you can parameterize a lot of things in these, but if you keep a lot of things internal, it lets the layout happen a little faster. It gives it a little more flexibility. So it's generally not good to just have a massive number of outputs that you don't actually need, or inputs. Oh, this is an interesting one. Yeah, we should do this because this will explain a little bit kind of what's going on here. So if we elaborate, can I really not? I don't know why I cannot make that bigger. If we elaborate this, what it's saying is take this Blinky module that we were looking at that's like this shorthand and turn it into like the full thing. Like take all the macros and run them. And you can see what it's doing. This is just a standard Elixir stuff. Like this is the module. This is the name of it. You can see here are these ports, and then the blocks of code, right? We had this, what is this one? This is the counter, it's synchronous, right? So this one has a clock, this one doesn't. So this is the combinational, and this one's the sequential, right? And then there's no params, but we'll get into params and instances too. And then black box is another kind of interesting thing we have time to talk about. But right, so this is it turning into like the intermediate Elixir representation of it. And then this somehow has to get into Yosis, right? So there's actually another step. Let's see. There, so we can emit what's called RTLIL. I don't know what that stands for. I call it RTLIL. But this is interesting because most of the other languages that I was looking at as a reference, they don't use this format. This format is actually a Yosis specific intermediate language. So that's what IL is on the end, obviously. All of them though have started to do this. Like you wouldn't want to take this Elixir code or whatever, or Python code or whatever, generate some AST and then try to like manually craft Verilog or system Verilog. It's super clunky. There's a lot of gotchas. And so there's like a couple different languages that have come out. I think one's called maybe Chips or something. Like Amaranth uses one version of some language. The one that Chisel uses is the one that's the most maintained. I can't remember what it's called, but I probably mentioned it in here somewhere. But anyway, they all go down to an intermediate language. So after the initial like AST generation, we go one level deeper and we get to something that Yosis can actually understand. So let me run. I can't remember which ones these are on. What happened to it? Two. Why did I not? All right. So we're going to emit the same one, and then we have this IL file that gets written out. And this is actually, and it's funny because it's actually a lot. It's pretty concise. Like when it's this simple, you can almost just look at it and just read it here. But this is essentially will work. You can take this and you could turn it into system Verilog, or you could turn it into Verilog. You could turn it into VHDL. It's kind of like the intermediate languages that like LLVM or something would use. So, but if you kind of like read through it, you can kind of see it's basically the same constructs we have, just kind of expanded out. Like you see here, like when I said, it's nice that we didn't have to specify the width of the one when we added it. Like this is why. And then let's see, do I have the other example? So yeah, there's our RTL, build, synthesize. Yeah, so we already did this. We built it, and we synthesized it, and we sort of watched it blink super fast. So let's look at this one. Talk a little more about the pipeline, right? So the pipeline is, like I said, we have this Elixir DSL using macros. We turned it into this intermediate representation. Obviously, there's some things that were inferred at the higher level that now have to get resolved down into like the actual numbers, like the widths have to be put places. That gets turned into RT lil. And then, so this is like the manual stuff. This is like I have code that takes this structure, walks through it, and generates this RT low code, and then that gets fed into Yosis. And from that point on, it's just normal like open source HDR stuff. There's nothing Elixir after that point. Let's see. I have. Yeah, you kind of see here, right, like the structs and stuff that get built. These are all the different operations. So there's a bunch of different convenience operations. Let's see. I think I have a map down here. I don't have them in here. I have them in the docs. But basically, when you do a bitwise and or bitwise or anything like that, you have to turn it into something that can actually get synthesized. And so these are all just showing like you have these binary options, or unary operands, right? Bit slices. All these things are like internal things that RTLil supports, and we just have ways of generating those using standard Elixir like macros and like this right here. So like if you do a plus here, it's obviously not just like adding these two things together. So under the hood, this gets looked at and generates a struct. I'll actually show here, but and then there's a bunch of other some of these I've removed. There's things that Elixir kind of doesn't support. Because I am kind of like essentially abusing the fact that there's like precedence. Actually, I might actually have a doc that can describe this. So you essentially have this precedence where like equal has the highest precedence. You can't override these ones. The kind of left arrow has one precedence, and then as you go down, it's like less and less. Like these things will get executed first, then these, then these, then these, then these. And so the problem is I chose, where's that squiggle operator here. So the squiggle operator is here, but that means that things like ands and ors to use for like bitwise, Elixir will try to resolve those in the wrong order. So if I use ands and ors, I have to like wrap them in parentheses. There's also a really annoying thing, which is that there are certain ones, I think it's this one and this one, those are bitwise and bitwise or, and Elixir just dropped support for those. Like they deprecated them, like I think in like one or two versions ago or something. So like if I try to use those, it will actually throw a warning. And so I use you'll see a band and bore in my code some places, which is basically a function representation of all of these. So right there. So let's see, go back to this pipeline. Okay. So what else can we look at in here? Yeah, so we saw the what this ends up looking like. I should have left it in here. So then we move into this Yosis stuff. The reason I also like some of these problems like are simple enough that you could almost just do it yourself. Like with a simple Blinky, you could figure out the exact Verilog and maybe even do the placing and routing yourself. But the thing that these things really give you is the optimizations and like the support for multiple architectures. So by targeting Yosis at this level, NextPNR has a lot of support to build the actual bytecode for a lot of families of FPGAs. So the nice thing about targeting at such a high level is that, say I were to like later change to 20s at different backend other than Yosis even, I just have to adjust to use their intermediate language. Or I could use Yosis, and Yosis can actually take its intermediate language, turn it into system Verilog, and then I can feed it into like the actual tool chains or something. So it's a really nice abstraction layer to just target at this high level, and then everything below it just kind of you stand on the shoulder of giants to do all this work, because this stuff's, especially the Ice 9 the Ice 40 chips and all that. Some of these things are terrible to work with. They are all proprietary. There's no great docs. Like you have to use like every time they release a new one, you've got to download some old version of the software. So the people who are doing this are like having to like essentially fuzz all of these options and then generate this like if I change this one option, the program does something over here, and they're essentially having to like, no, they're not legally speaking, because you can't do this. You can't reverse engineer the code, but they're effectively taking a million inputs and then seeing what all the ones and zeros are at the output and saying, okay, if we do this in our code, we need it to generate the same thing. So they're effectively making a bunch of test cases. So it's almost like distilling a model. So I'm assuming that the reason why a lot of this stuff has moved on so fast recently is that AI has allowed people to just, ask a simple question and have it look at it and say, yeah, like dig down into all the numbers and say, here's the pattern. So, and then this is kind of where it gets really interesting and really convenient is this ability to define boards, like reusable boards. Like if you were making this for like your own chip, you wouldn't necessarily get to this level. But a lot of people are messing with this. They have the same, one of maybe 100 different development kits or something. And so once one person defines this becomes shareable in a library, and then anybody can just use it and refer to something as LED 0 instead of having to like map it to the actual like pin that's on the device on the chip, and knowing that like the clock frequency is 27 megahertz or all this stuff. It's great because this becomes super shareable, and what these compile down into is different for each manufacturer. So, and it's nice because NextPNR can generate these things. So I can tell it like, okay, go in, which is the one we'll look at in a second. The board we just looked at, by the way, is made from a company called Cyped. It's called the Tang Primer, but I have like a Tang Nano. There's a Tang Console. There's a bunch of really nice, low cost, pretty well supported open source boards. Or no, they're not necessarily open source. They support open source software. None of them are really open source. But they use this thing called a constraint something. I don't know what the ST stands for, but it's a constraint file, and it's in one format. If you use the ICE 40 boards, which I have one of these we'll look at, they use a PCF file. So these are all three different companies, right? And this is where, like, I don't want to deal with like all of these things. And so it's nice to be like, if anybody's using just this board file, they can calculate these, like on demand. You don't have to like make one. This just easily makes the exact right pin output to feed into NextPNR. So I'm going to dig a little bit into, I want to cover a little bit of combinational sequential stuff, and then maybe, I don't know how much time. Yeah, now about halfway through, and a little less than halfway through here. So we'll speed through kind of some of these. But I want to get to, I have some really cool stuff that I didn't even get a chance to put in these slides that I wanted to look at. Combinatorial logic, right? So it says here, it's the simplest kind of logic, right? So there's no clock, there's no memory, there's no state. So it's just purely like the purest function. You give certain number, you give some inputs, you get an output. So in this case, it's just a simple adder, meaning it's essentially acting like almost like an AND gate, but an AND gate for bits. So in this case, each one of these is 8 bits wide. So if you were to map this on something and have 2 buttons, and then you press the buttons, you're gonna like, I don't know, send some number, like one button's gonna send 5, and the other button's gonna send 10, then the output would produce 15. So there's a way I thought about trying to produce this, and I'm glad I didn't, because you probably wouldn't even be able to see it on the camera. But essentially, you can think of these as essentially instant. As soon as you press them, it just happens under the hood. It's not even tied to the clock. It just happens as soon as the electrons move. And then, yeah, it's nice the translation of what that looks like. Not actually that different, right? You're just straight up connecting, A to B and to Y. Y is the output here. So, and then having to specify the widths. So this is actually not that hard to generate. This is where it gets kind of interesting, is having something like an arithmetic logic unit. So in this case, what this does is define a few different operands. So this is, 0 would represent add, 1 represents subtract, right? So it's like building a little piece of a CPU here and saying, depending on what operand I give you here, and that's like, so that's 3 bits. And I'm going to give you two 16-bit, numbers, and then you're going to calculate this output, and you're also going to, in the case of I think 0 might produce, subtractions or something, you could go below 0, or if in this case, right, it's just saying the output is 0, so make that 0. So yeah, this is all that would look like. You would just have this little, what looks kind of like it is a case statement. These are essentially just like putting the numbers here, but it would be annoying to put 0B, 0, 0 here, and it's a little easier to refer them as add. There is, there's another version of this later for sequential that looks better. So do I get into here? So yeah, the operators we can use, and like this is a bitwise and, gets translated into this for RTIL, RTLIL. Bitwise or bit shifting left and right. I think there's actually, so there's shift left, shift right. Let's see. The 0 flag here. So the default case is what that was. So the default case here, it becomes so it falls through here, and then that becomes out, and then 0 will always be just this out. So that was the default case here. So in this case, 0 will always just be whether that is 0. And then it goes through that. And the sequential logic, we've already basically covered this, so I'm going to skip over this because I want to get to the FSM part of it. This is like the exact same case we've been looking at. Again, the key is that this has a clock. And so all of these are going to have clocks coming in to gate them. We'll get into later, I think I mentioned in here somewhere, we'll look at it in the other components, the cores. One of the problems you run into with hardware like this is that you might have multiple clocks. Meaning you might have one thing that's running, say, once a second. You might have one thing that's running like at the fastest it can at the system clock. And so one of the kind of critical or I guess foot cannons you get into is crossing clock boundaries. So that's fun. So if you imagine this output here, or sorry, not the output, the count here, this is being updated at whatever the clock frequency is here. So if you had another clock frequency that's half as fast, or maybe half as fast might not be as bad because it might just work. Say it was like a third, right? So sometimes the things like transitioning right as this thing's trying to read, you get in a case where like the thing will be like for it to read what the value is, the thing has to be high or low for a certain amount of time. And if the thing's like right in the middle of transitioning, right as the thing tries to read it, you'll get kind of like unknown behavior. I think I'm going to lead you wrong. Pretty sure they refer to that as metastability, where like it might most of the time work, and then every now and then it's kind of like a flaky bug in a test where it just like every now and then it'll just like freak out because like it catches it at just the right time. Let's see, skip over that. Yeah, so the critical thing to be able to like reuse a lot of this stuff, which I was really not sure how I was going to get working in Elixir, is most modules are essentially generic. So you might say, like in this case, I have a counter, and I want the counter to get a count up. I want an 8-bit counter, or I want a 16-bit counter, a 32-bit counter. And so in most languages, you can imagine you might be like, oh, you have a T counter, and then that T would get used like here or somewhere, right? Like you would basically refer to this in some generic way, and that allows you to say, well, I'm going to define one counter, and then any number of bits you need. You can just like override it in a generic way. Well, the way that I accomplish that here is just with this param that comes in, and then anywhere you need to use the generic param, you just call it like this, and under the hood that gets turned into an attribute. So you can call it this way. So anyway, it actually turned out to be a really simple problem that I kind of initially racked my brain about, like how this would work. But turned out to be super easy because Elixir, seems like a standard pattern that would exist. Like it doesn't, there's nothing crazy about it. Like it almost makes you think that people are using generics for this or way overcomplicating it. And then let's see. I'll get into memory. It's a good one. Might just skip over this part. It's just more of the same, and I want to get to some of the examples. But let's see, register file. Disconnect. Yeah, okay. So depending on how the FPGA is set up, one of the other parameters you get to play with, or one of the other kind of like limiting factors, when I said you have LUTs and you have to meet your timing requirements, they all also have a certain amount of RAM baked into the chip. Because it'd be really inefficient to try to like use, even though you could like technically you could build RAM with a flip-flop, you don't want to because those are really expensive. If you think about it, you have 20,000 LUTs, and that sounds like a lot, and you can do a lot of cool stuff. But if you use if you want 10 kilobits of RAM, 10 kilobits, right? Like then you're going to use up half of your LUTs for it. And so they all bake a certain amount of RAM kind of spread throughout the board. It's in blocks. I don't remember if it says in this one how, but it'll be like, there'll be like 8, or something like 16 bytes over here and 16 bytes over here. And they kind of spread it out of the board so that you can just use a little bit of memory where you need it without having to waste your LUTs on it. So there's a special macro for using that called memory. And so in this case, I'm saying I need like an 8 wide, 4 deep chunk of memory to use, so that I can just write stuff to. So yeah, here it's just writing in. So it's just acting like a register. So this is a good example. Yeah, so is that a better one? Yeah, so this is called the lookup table. So okay, so yeah, in this case, you can think of it like a 7-digit display, like based off the input number, which you really just want to, if you're going to return a number for a 7-bit display, you really just want to give it a 1 or 2 or 3 or 4, right? You don't want to have to have the person tell you what specific segments are on. And so this thing is basically being used to store all the values that essentially the font for what that would mean to have a 1, like which chunks of these things are on or off at a given time. And then all you're doing here is just saying, well, based off of the looking up of this hex number inside of this LUT, set that to the segment. So I don't think this actually covers, this doesn't cover the actual loading of what's in here, right? Because obviously something has to get into this memory, like the pattern of which pins are where. So you'd see here, right? Like this here, X0 would be like this, right? So like all the corners are on, I think, and just the middle line is off. So let's see. Oh yeah, delay lines. This is gonna. I don't think it actually shows what it says it shows. But let me skip off of that one, and we'll go to So this isn't the async FIFO, but this is just a FIFO that just writes to memory, and then on a clock pushes things onto memory and then pops things off of memory. There's another version of this called an async clock, an async FIFO, which would be this is like the way that I said if you're crossing clock boundaries, you can't really read off of one to another. If you use a FIFO or specific an async FIFO, you can have 2 different clocks on it, and then one side of the clock frequency you can pull off and the other one's writing onto it. So I thought that was really interesting. It almost, if you want to think about it in like web terms, it's like having a pub sub message queue where it's like one side might just be throwing things on it 10x, and the other side's just a little slower pulling them off. But obviously the amount of buffer space you have is going to limit that. And then for I didn't really give a good example of this here, but you'll get a lot of help from the system if you try to use some memory, or you do something that tries to use memory, but you code it in the wrong way. This actually protects you a little bit. But if you're normally in Verilog, if you I don't think what the example was specifically. if you do things wrong, it'll go, well, I can't use the RAM, this your built-in SD-RAM, so I'll just construct the whole thing out of LUTs. And you'll usually know that it did that because your build will fail because it will like run out of LUTs. But the nice thing about Elixir again is that this like ensures that you're going to get memory out of this. It's not going to like accidentally turn into LUTs. So I thought that was another really interesting side effect. Most of the other high-level synthesis languages like Amaranth and stuff, they kind of do the same thing. So that's just a really difference between system Verilog. This was a really interesting. I don't even know. I think I came up with like a example that needed this, and I wasn't sure whether I was going to like bake it in as a macro or just use it as like a component, but I just decided to leave it in here. Before we had this something like this, right, where we have a case statement and just some like numbers, and it's in a sequential block. And what you're effectively doing is saying like, based off of this light value, which is not showing here, but there's, you can imagine there's an input called light. If it's 0, do this thing. If it's 1, do this thing. If it's 2, do this thing. And then what it's doing, you can see internally, is it's saying, okay, well, do something and then set the light to 1. And then do something here and set the light to 2. And then do something here and set the light to 0. So you can kind of see what this is doing. It's like looping through and saying 1 goes to 2, 2 goes back to 0, 0 goes to... Right, so it's acting like a state machine. And it's pretty verbose to do it this way because you've got to, like, everything has to manually do this and then key off and, like, be setting the light. And so because the macro system is so powerful, you can kind of just essentially get it for free by keying off of the state itself, which is coming from light. So let's see. The state is red. Yeah. So the output becomes red, green, or yellow. Where was the... Sorry, I'm missing something here. I think this example got changed and it should have been timer, I think. Timer state. Hold on, let me look at this other example. I think this one got jacked up. I know this other one works. I don't want to. In here in examples, traffic light. Yeah. So, oh no, okay, that is right. My bad. Okay, so so you're saying this state is red. So set the red to 1, set the yellow to 0, or green. So it's just one hot. Actually, now that I look at this, there's a nicer way that I could have set this. But this is, I guess, a little more explicit. But yeah, setting one of only one of them active. The downside of doing it this way, though, is think about it. I could accidentally set 2 of them, and so like there's better ways to do like a one hot encoding than this. But anyway, the other part that's a little janky about this one is having to manually increment the timer in each one of these. I need to figure out a way where I can basically say like an always, because really I want these to like go through and then at the end just say yeah, and then increment the timer for everything. And then also, yeah, you notice every one of them sets the timer back equal to 0. So there's a couple things that I could probably reuse here. But yeah, the other thing I did recently with this one that the other one didn't have, so I guess it's good to look at. 6. Yeah, so 6 and 2. So notice this one, the only inputs and outputs I had were these. This new one that I updated, I added params, which basically let me say something like how many number of ticks it will stay red, how many number of ticks it will stay green, how many ticks will stay yellow. So that was a little nicer for some of these demos because it's hard to tell. Because I actually ran out of yellow LEDs, so I only have red and green. And then some of these boards I only have amber, so it was hard to tell whether it was on a red or green or blue. So I just set the timing. And then let's see. Most of this I put together to essentially act as documentation for Claude, which actually was super convenient, but it's a little bit verbose. But it'll eventually make good documentation for the repo. This is another one I couldn't find a good example to try to use this with because I didn't hook up anything like Ethernet or HDMI that would have really helped with this. I used SPI in a couple places, but I was doing it in a way that wouldn't work. But one of the things that's a little annoying, I don't know if I have a great example of this here, but like if we look at something like, what's one SPI bundle? Yeah, well, I was just using a bundle, so of course it's going to be that. Maybe the, oh, I know why, because it's not here, it's in course. I'm not gonna find it. Okay, actually, yeah, you can kind of see here. I really not. It's weird. I can set this one. I can't set the other one. Some of these lines, right? Like, say in here, I'm going to basically say like, this is the SPI controller, and you have this clock select line and this busy line, a done line, and like the data out, and like all of this stuff. For the most part, like when you have communication between these like different, like a different protocol, like you might have it's like I squared C, I squared S, HDMI, anything. You have a certain set of cables, and they have a certain directionality. And you're always going to use the same pins, and then you're always going to say, well, when you called it input, I called it output on my end. And when you called it output, that was my input. Or you'll use like TX and RX for transmit and receive. And it's really easy to get like something like the widths wrong, or just the name wrong, or like not wire one up. And so one of these convenience features that a lot of the higher level languages have is some way of grouping like a common interface to a set of cables, and then automatically doing things like flipping the direction. So in this case, this one's doing an SPI, which is serial peripheral interface. So it's like a pretty fast interface. I think in one of the examples we're looking at, the screen that I'm using is based off of this. Actually, the SD card readers, they use SPI, and they actually use SPI in two different ways, because they use one at a slow clock rate to first initialize it, and then they read it as fast as they can. So you actually end up needing like two different ones, because one's running at one frequency and one's running at another. You also have this idea of the master slave. This one's not actually showing. This one's just showing the master side, but the master one's like controlling the actual traffic. And then you can have a bunch of other devices you're connecting to, and you use a select line, which I don't think they show here. That's the clock line. That's the input, yeah, select right here. So chip select is the CS. So depending on what device you want to read from, you put its pin high, and then now when you read, only that one will respond. And anyway, so all of that stuff is like a little annoying to have to remember, and so it's nice to just say, hey, I have this bundle here called SPI, and SPI has a bunch of wires in it. And so now you can just read them like this, and you can group them, and then when you connect it to the other end, it automatically flips, so like it knows the difference between input and output. So see, that's a good example. Yeah, and at compile time, obviously this has to all expand out. This is just like a convenience for like when you're looking at it while you're writing it, or somebody might define some shared set of interfaces in a common way, and probably even put those in some cores that are shared, and then all you have to do in your design is say, I just use this specific bundle that's compatible with all these cores, and then you get cool dot syntax. Most of the other libraries, like I think bundle is the exact name that Chisel uses, but most of the other ones have something very similar to bundles in their language. Yeah, so they solved the interface contract problem, which is, again, it's one thing when you say I have one of them, but there are like one of these boards that I'm looking at has like, I don't know, like 3 different parallel lines. It has these things called PMODs, which each have like 10 pins, and then it has an HDMI and Ethernet. If you think about wiring all those pins up, it's much nicer to think about it like a cable than to think about it in terms of every single pin, because some of these parallel lines have like 40 pins. What is this? Instances. Okay, so this is where like the real power of like open source HDLs like come in, is via the ability to share components. Like one person defines a library, and somebody else says, oh, I just want a counter, so just use the counter, and then give the params, and then hook up my clock lines. And you can imagine this could be anything. This could be like the HDMI, like protocol part of it, the HDMI core that actually knows how to really deal with HDMI. And this board has an HDMI port. You just are going to hook up some lines to it, and it'll just do the right thing. What's another good one? Like different displays. Like we'll look at one of the displays here. They all have different chips that have different drivers that have slightly different like protocols for like what pin does what and like how you set the backlight brightness or whatever it is. And so the nice thing is somebody can define this for you, and then all you have to do is give the parameters, which are again like that kind of think about the generic arguments, and then the actual like pin hookup. And this is much easier to read than like trying to splat out this into every one of your files. Yeah, so you can see here like is saying what it is. So the instance here, this names it. So this is what you're going to refer to it as in your design. And then all the port connections. And what was this one? Oh yeah, this is something I ran into, so I added it. Sometimes you have to hook up all the pins. You can't just like leave one floating, because if you did, like the reset pin floating might sit there, hover at like 0.5 or whatever. Say you're at 3.3 volt logic, it might sit there and hover, and then every now and then be considered high and like reset your board. And so a lot of the build tools will be like, hey, this pin's unhooked. You need to either tie it to ground or tie it to the highest high voltage. Anyway, so I have a way of just setting it to a constant value. And that's just pretty convenient for things like this, where I just don't want a reset pin hooked up. And then, yeah, and the rest of the compilation just happens the same way. I don't know if I'm going to go into, yeah, this is mostly just funny things about Yosis. Yeah, that was one of the ones where Yosis has a lot of weird things where like if you write something the wrong way, so like it might like in this case it might truncate it or just put it in the wrong place. So like if this counter was actually like an 8-bit thing and it said 6 here, and then I did this, you might be like, oh well, that's fine, that's like six numbers, but that doesn't necessarily mean it's going to do the right thing. What it might do to make this 6 is do like that and just cut yours off the end, or make it 8. So anyway, it's just you have to be very explicit about it. So the tooling doesn't actually like catch all of the errors. So it's nice in the Elixir code because it's all happening at a macro level. It's all happening at compile time. Like all the checking I want can be done then. There's a couple other places where I don't think I got time to do it, but I thought that'd be really good to be able to use Elixir's what is it called? The bitwise deconstruction, right? Like there's other things in Elixir that might be really nice for constructing large pieces of this and doing like pattern matching that I haven't gotten to or like figured out how that would actually get synthesized. But yeah, right, I'm gonna skip through most of this because it's just mostly how to use the tools, and we'll just look at some of the examples. Traffic light one might actually work because it'll be slow enough for the camera to actually pick it up. So 202. I can't hide. Oh, right. That's the cores. I'll look at that. Look at Hardwire. Really can't do that. It's really annoying. Okay. So there's a couple other examples. Cool thing is I don't actually need this one. At first, I had this traffic light example, which is basically going to have 3 different color lights, which on the board it's going to be all 3 the same color, but 3 lights, and they kind of like act like traffic light, like stop goes, and then eventually they'll go to the green light, and then it kind of hits the yellow light kind of quickly, and then goes back to the red light. And the red light's a little longer than everything, obviously, because we're always stuck at a red light. I had composed it so that the traffic light got pulled into here. And the reason why is that I want the clock and the traffic light to essentially be happening on seconds. Like I don't want internally for this thing to have to like divide everything by like 16 million or something. Or like if you use this traffic light on one board that has a 27 megahertz clock, and you've baked in all the right numbers in here to make it so that the divider is right, so that it sits for exactly 10 seconds, and then you use it on another board that has a 40 megahertz clock, it's going to go like almost twice as fast. And so the nice thing is to, you make the modules, these modules are super reusable. And then the module that you're actually going to really use for your project. A lot of people call them top. They'll say it's like it's essentially the main file. This one might have very specific information about your board. In my case, 23 is this prescaler value that gets this like a 16 megahertz clock to 1 hertz, or gets a 27 megahertz clock to about 8.8 hertz or something. We'll see later. I have a much better way of doing this now. But essentially, like this one is very specific to one board, to specifically the primer 20K we're looking at. But the module underneath it is super generic. So that's nice. That's one of the nice things about composability. So we'll try to flash. I think what we'll do is we'll flash. I think we can flash this one now and give it for RAMs. Which one was it? Yeah, this one. Yeah, I want to use the PX. I forgot a couple of things. I deleted I guess I deleted the one that was working for the one that I had. So let me go back to here. So what we need is we want the traffic light top. The border is the primer 20K. And then this port map should work. So this is saying, right, so we use the system clock. Our red is 0, yellow is 1, green is 2. And then the params here are just setting essentially this is essentially setting how long the lights are going to light up. And I'm going to sit at this value just so we can see it actually working. But then we'll play around with the numbers, make sure it's actually doing what it's supposed to do. And then now you got to program. It's very similar, but we use that. And instead of, and you don't have to give obviously the constraints anymore. You just need to tell it what board, and this is so it knows what programmer to use. So that's programming it. Let's see. Did you do the thing? Or are they off too much? Oh, I really hate doing this here. So you know what I'm gonna do? There was another part of this that I'm just gonna skip to because this part sucks. I really hate, so even though these tools are nice, right? It's still pretty error prone to like have to manually go, okay, like what LED am I hooking this up to? What's the prescaler? How does that scale? So if I want it to be a second, like what do I have to set this to get it to a second? And so what I was thinking is, like using Elixir is nice, using Phoenix is better. So in this, here, I'm running out of, let's see, you think is this 4002. Basically made a little Phoenix app that is, so it's running locally, right? Obviously this isn't going to work as a web server for other people to use. But it's looking at the device plugged in, so like unplug this device. Come on, there you go. So it'll eventually recognize that the thing is unplugged. Plug it back in, it'll tell me which one of them is plugged in. Right, so this is still it's a 10 nano. It's not saying exactly which one, but this is the primer, right? And then instead of having to like do all the code, we can instead say, okay, we have the 20K here. Here's all the output pins. What we need is the system clock, and what we wanted to build was the traffic light. There's a couple different ways I could do this, right? I have the top here also show up. And so what I could do is set the prescale. Actually, let's do that one first, because that's simpler conceptually, and this would just work. So the pins for the LED are here. These things are terrible to click. And then I have the clock way over here, so this clock over here. So if I like try to like loop it all around, it's kind of annoying. And so what I added was the ability to like move the pins to the side. So now I can put the clock here, and this will kind of, yeah. So essentially this is what we're doing. And so now I can just say, well, build it. And it put all the right values in the right places. It knows because of the board, it knows exactly how to configure it. And then way down here, okay, it's still generating output. Way down here. it generated that design. And then if I click flash, it just flashed the design. So let's see. Yeah, so now it's working. So let me go back to, not. I put you get on 7, right? Apparently not. What screen did I put that on? Where did Zoom go? Let me stop sharing. There we go. So yeah, now you see what this is doing. It'll change here in a second. There, it's hard to see because it's so bright. But yeah, so it's just cycling through and doing like a red light, green light. So I'm gonna do real quick. So you guys can't see my camera, right? When I'm sharing. Is that right? Or can I just, because I can't see my camera when I'm sharing. So
we can see your camera when you're sharing, but on this big screen, you're like tiny over on the side.
Okay. So yeah, we'll lower this down. So that internally, those are using, like we were saying, it was like the default is like a 10-second red light. This is about so there's 10 seconds. Instead, I wanted to be about 5. I could lower this down and then build. This you actually usually built a lot faster. It's building a lot slower now because I'm screen sharing apparently. And now it'll be like, yeah, it's twice as fast, but it's still like not super fast. So it's like put down like 20. Wanted to get to where like you could literally see it flashing. There. Okay. Flash. There. But now you can probably see it a little better, right? Where it's like flashing pretty regularly. This one here. Right. So that's kind of interesting, but it's the most interesting part about this is that that the other component I wrote, or these components here, allowed you to build up a much more complicated design. So like I said before, it was a little annoying to have to like just figure out what the number would be to make it the right count. And so what instead I did with this was say we have certain parameters about the board that get output from it. One of them is the clock cycle or the clock frequency. And so I can grab this, frequency over here and feed that. I haven't added the thing to adjust these left and right, but you can see over here, it's basically saying, okay, your clock is 27 megahertz. You want a 1 second period. So therefore, this is the half period that you need to feed into here. And then now you can get a clock out that will happen at like exactly 1 second. And you don't have to think about it. You have to change this to be a different board and just know it's megahertz and then it would be automatic. And then the other thing I can do with this now is because like I said, I parameterize these inputs, I can make those, I can just change them on the fly. I think we can build those. It'll be pretty quick. I need to make this float to the bottom, but yeah, there's a decent amount of stuff that actually happens with this. It's impressive that it all works as well as it does. Yeah, so now flash that, it loads it on the RAM, and then now I got the same lights, right? So let me actually see if I can. So now we're going to use basically the same program. Oh, actually, I just realized I can't use the same program because I have it here. But you can see this tiny FPGA. That's this other chip here. You're not going to see very much of it, but it's a much tinier, very cheap FPGA. So we're going to program the exact same component, like the exact same module, and should just be able to change out just the board. So actually what I'm going to do is, it's a better way to do this. I don't have a way of copying the module, so we're going to go down into here, and I'm going to copy. So I have these projects just output based off your environment into like a folder here. So the only files that are actually getting put in there are like simulation files. There's the build file, and the design file is just a big JSON file. So we're going to grab that primer counter and then rename it to tiny traffic 2. Now I reload this, I think. Or if yeah. And what we do is we just delete this and then add this one and move that clock over. And the pieces we need, right? We need to hook up these RGB LEDs. And so this one, oh wait, I can look at the other one as an example. Let me say this real quick. The difference with this one is that this board doesn't have LEDs baked into the board. I had to like put them on and add them to like GPIO pins. And so what I added was, let's see, I'll go to time traffic, was the ability to like have GPIO pins like this defined. And so there's like a bunch, there's 31 pins. So say I defined 3, 4, 5. Let's say I wanted to add 6. I want that to be an output. You can invert them from here too. But say I add it. Well, now I have another pin here, right? So then I can go ahead and remove it. So that's basically what we do. We have to add these pins with their GPIO pins. So come back to traffic 2. Come in here and say 3 output, 4 output. All right, so 3, 4, and 5 are those pins. We're going to hook those up to these RGB. I think it's 3, yeah. Try to remember which one I hooked up to 3. Yeah, 3 is right. Okay. All right, and then this system clock needs to feed into this system clock. I'll need a reset also. Where did I put the reset? Reset is on 1. I'm going to do another output pin on 1. Hook that up to the reset. Oh, no. Oh, I can't. That's annoying. It won't let me see what I can do. If I leave it off, it's going to be really annoying about it. Let's see what it'll build. All right, so yeah, this is telling. So there's a bug in the front end here, where basically it's trying to type check these, and it's figuring out that it's not thinking that they're the same type, even though they should be. So what I can do is just hook this up to something. Come on. Can I hook up to you? No, broke. Okay. Well, I guess we'll have to go to the other one. Okay. Gotta be a way around this. From here to here, from here to there. What if I put where that should have worked? Because it's not letting me hook up to anything. Usually it'll. Well, there goes that. Let's look at this other one. So how is it doing? Oh, because it doesn't have a reset pin. So why did that one work? Oh, because there's a button on the board. Yeah. So it's basically it's letting me hook it up to these, to this button because it's an actual button type. So it's because I was too type safe. I'm not going to hook it up there. Anyway, well, we can look at this one, right? So we can build that one, and then this one's actually a different USB cord. Where's it at?
You spent a lot of time trying to get lights to blink.
Oh yeah, it gets better. How much longer are we at? For about 10 minutes. Right, let me flash this. Oh. So USB cord is super finicky. There we go. So let's see. So, that's handy. Yeah, so you can kind of see this one. There's a green light, yellow light, red light, right? So same underlying like this one, I had to use the top file for it. I really wanted to be able to, like, if I can get the reset to work there. The idea is I don't want to have to write top files if I'm using the Visual Builder because I don't need them. Like the actual like wiring up is all that the top file does, and so these wires are essentially acting like the top file. And I had this idea that I might want to write code, so I added each one of these has a block where it can have a custom code, but I'm not going to get there yet. All right, so the last thing I'm going to show, I was really hoping I could do this in the visual language, and I thought it'd be really amazing, but way too complicated. Let me show you another example of how crazy you can get with this. Let's see. There we go. So this is a Game Boy emulator written in Elixir. So the Game Boys are made up of a few different parts. One of them we already know, right? So where's the CPU, right? So we have an ALU. But just like we were showing before, we have a pretty simple ALU. And now you've like seen that, like this code probably looks like, especially up here, right? Right, you have these are your inputs. Here's your operand. There's some other selectors and stuff like that. There's I think these are essentially like DMA. But a lot of this is based off of like there are many Game Boy emulators written in like WebAssembly and C and whatever. It's much harder though when you convert it down into the actual FPGA code. There's only a few open source ones. Most of the ones you see are actually like closed source because they're making money off of them. So if you see a Game Boy emulator that's an FPGA, it's very likely it was a closed source core. There's only a few that are open. So a lot of this, I initially tried to base it off of some Super NES ones because the Super NES and the Game Boy share a very similar CPU. But it was too hard to decipher. And so I ended up basically saying, just scrap that, go back to just, there are some super old docs from like 15 years ago that are like the exact inner workings of the Game Boy. And between Claude and me just documenting everything as a tutorial. So like, where's that in here? Oh, it's not in this one. So the first one was writing it in Verilog. So this version, the Game Boy Go Win, is a version where I basically just had Claude come through and say, do these tutorials. And then I was implementing the code. And then eventually I got down where it was pretty complicated and Claude had to just implement everything. But the problem with this one is it's unique to the Go Win. It's unique to the Tang Nanos. And the whole point was to write one that could run anywhere. And so as I started writing this Elixir one, I realized, well, this one's nice because there's literally the only thing that really matters is like whether you have the right number of output pins and you have the correct number of LUTs to store this stuff and a certain amount of RAM. So anyway, it gets much more complicated, but between Claude and enough research, it's pretty easy to get these things to write out. This is one of the harder problems is getting you can get the actual like processing of it to work. Like the CPU part is actually one of the easier parts. Things like sound and the screen and memory banks are much harder. Spent a lot of time on the screen and just barely got it working. But again, it uses the SPI interface. It's a little weird that I wasn't able to use the bundles with this one, and it was mostly because the way this got architected with Claude, I didn't want to tear it apart. It kind of mangled or mixed in how the Game Boy wanted to talk to an interface, plus how the interface talks, and I need to separate those anyway because I have another thing I want to use this for. So at some point I'll be using bundles for this. But other than that, it's not too complicated. Like this stuff is the stuff that is very specific to each display you get. Like each display is going to have their own little set of like commands you have to send to do certain things, like like essentially to basically reset and say I'm going to start sending you bits from like the top and go down, or what you set the backlight to a certain amount or whatever, or set what your clock cycle is going to be, like how fast you're going to run. Yeah, and then there's just a giant state machine, which this actually could, like, so this here, right? Notice what it's doing. It's saying sequential, and it's got a number, and then it's setting a state. So I need to replace this with an FSM now that I have that done. And this whole thing, which it wouldn't be that much simpler, like unless I can get the default case stuff so that I can set the other things in like a default area or something, then it doesn't actually remove a ton of code. It just becomes a little cleaner to see. Oh, well, like 0 is kind of hard to read. Like this should actually really be named some variable. Anyway, all right. So let's see this actually running on a device. So this is where I was going to use this other camera, but I think that my camera, this laptop, is actually working a lot faster. So what I'm going to do is swap these. All right. So all we're going to do here, I've already built it because I will say, we'll build it after this, so I'll show you what I mean. I'm just going to program it, and we'll just see how it works, and then I'll show you how the building works. So the actual programming part of it's like super fast though. And that's it, right? Just taking a bit stream that's like how big is this thing? It's not very big. I imagine it's like 16 kilobytes. No, it's like 7 megabytes. Oh yeah. Well, because like I was saying, it's actually a lot bigger than it should be because it's just a bunch of ones and zeros like as text, and which is like the weirdest way to try to save something like that. All right, so let me switch here to, oh yeah, I gotta stop sharing. I wanted to switch my camera to this other one that's better quality. Will it work?
No.
Will it blend?
No.
Hello.
Hello.
Probably just doesn't have like the, you know what, I tried this out. I know it worked before. Okay, well. Oh, literally, it's like, that's so funny.
What's behind camera number 2?
It's really annoying. Well, whatever. This will be okay, I guess. Anyway, so do it this way, and we won't be able to see anything because, oh, come on.
It's too bright.
Yeah. Well, let me see if it'll. Yeah, see, because it won't actually dim. We'll do it this way. That's what I was going to try and use the other camera. It was way better at actually seeing this. Let's see. No, it's not going to. Well, that's really annoying that it's like I can't see anything. All right, what I'm gonna do is I'm gonna select something, because then I can probably dim it. You can kind of. Oh, come on, really? This camera sucks. All right, let me fix the other camera because this is not gonna work. This is what I was messing with before we jumped on the call, and it turned on. So I'm surprised that now it's. Oh, that's why. Because we'll have to do it this way. So I guess what it is Zoom doesn't want to see it, but which is weird because my. Maybe it just does not like it at all. There we go. Oh, it's that far behind, huh? Oh, come on. Let's try OBS.
Doing it live.
Yeah.
Can we ask that AI
You could.
how to like mess with the cameras to be able to?
Oh, that's a lot better.
Yeah.
Yeah.
Maybe done.
I don't know if it'd be better to shut off my screen or shut off my lights or turn them brighter.
You can see your screen if you're not sharing your screen if you think you're showing us via camera via screen.
Oh, that's right. Start virtual. Wait, so you can't see OBS here?
No, I see.
Oh, that's right. That's right. That's right. Because where is Zoom at? Okay.
I'm just gonna look at it.
Make it bigger. All right. This is what I was saying. This is what I was saying about how it wouldn't focus.
I see it.
This is Blair.
it's gonna be big. There's a light directly above this thing, so it's gonna be a pain. Let me oh, of course it's not gonna meeting. You focus on my hand. Like, this is the crazy thing. I put my hand here, and it will gladly focus just directly on my hand. But that is, it's like, nope, not gonna do it.
All right.
Anyway, so the idea is there's
Yeah.
a menu in here, right? And so the menu is selecting Game Boy games. So if I select one, so this is, you will do it. Come on. Yeah. Instead, zoom out. This is what I was fiddling with before, and there's nothing I can do. These cameras do not allow you to autofocus.
Can you turn the lights off in the room?
Yeah, if I turn the lights off, though, it just does that.
That's too bright.
It's like the same brightness. So what I was hoping was I could. Just turn this one. Just turn this one up. I think it's actually the opposite, where it's like I really want to turn it brighter. Yeah, and see, then you can see more. But anyway, yeah, that sucks. If I put this on a better display, it might help. But do I have?
I guess I'll flash up like really tiny Tetris.
Yeah, I don't know. Just can't get it to focus.
Have you asked?
But I get like way the heck down.
Oh, there it is. You almost had it. Almost had it. There it is.
There it
That's
is.
Oh!
Oh, now it looks good. Whoop.
It is a Game Boy emulator.
Add it to a
All
clock
right,
scale.
so
Sorry.
Oh, it focused and shot out just then. Dang.
I'm resetting it. All right, so I was trying to see if I could get, yeah, so it's like, it'll focus on the Tetris part of it, but like, I get it to focus on the letters. Come on, you can do it, little buddy. No. All right, so the one I've been working on is the Pokemon one.
Oh, you got Pokemon running on it?
Yeah, I'm surprised the audio should be better right now, but come on. Yeah, now it's making me crap.
Well, it was worth it. I was waiting to where this 2.5 hours was going to go, but now I know, or 2 hours.
I see it. I see it.
Yeah,
Yep.
especially little fuzzy Pokemons.
We have Elixir compiling the FPGA running Pokemon.
Yeah. I have to get a better camera.
Gotta catch
I
them
really
all.
thought this was going to be and it's funny. I could get it like literally down into its face and still like trying.
How many LUTs you got?
Oh, last one is-
Autofocus, man. What a jerk.
I see triangle.
I was trying. Okay, there. See, I should have just
Yeah.
done it that way.
Bouchon.
Yeah, tell me. Well, actually, yeah, there you go.
Oh, it's your mouse,
Yeah.
not an accent. It looks like an accent. That's hilarious.
So, that one.
What's LSD?
There's a thing that my friend pointed me to. That's a music. It's like a DIY. Not what's that? Like a not a bootleg game. What's the word? Homebrew game. It is. It does sound. It's like a. What's the word? It's like a Fruity Loops, but for Game Boy. So you can make sound. You can make music and stuff. And the reason why I got it was that it'll help me debug some of the sound issues that I'm having. Actually, I'm very surprised you can't hear the audio, huh?
No.
Let's see if I can.
I hear it in my head. Because it played like hours and hours of Tetris. So
I'm going to try this. I'm going to say start a virtual camera. Yeah, right. And then see if we can do this with it. So let's say stop sharing. Now.
Nice.
Oh, yeah. Get a.
Flip it. You can do it.
All right. Now you just need to program AI to break the world record.
Wasn't the like game like crash or something at some point? Can't remember.
Hear it?
I can't hear it.
Oh.
But I believe you.
I don't think the microphone's picking up with it.
It's probably noise canceling. It's probably filtering it out.
Yeah. Anyway, so yeah, there's a couple of weird things with this. Like you can see on the right side. Well, the thing here. Anyway, on your left side, there's a vertical white line, which is like actually the off-screen one. Other than that, it's interesting. It works. Yeah.
Now the microphone's not picking you up. All right, that's awesome.
Now you can. Oh, actually, I hear it. You hear that? Anyway, hello? Can you hear me?
Yep.
Okay. Sorry. Anyway, yeah, so
Is this open source? Can we download it and play with it if we build our own hardware?
I don't think I haven't hit the button, but I'm totally willing to do that if anybody wants to give it a try. The hardest part is setting up. Come on, where's my camera? The hardest part is setting up the tooling. So actually, real quick, I'll show you. I did try to document that because that's where the dragons are. So in here, there's a mize file. So I didn't want to use mize for like I want mixed tests for everything. But if you go in the mize file, you can see certain things like how to get the depths. You obviously it's going to work if you have Pac-Man. If you're on like Arch or anything like Arch, it'll just work out of the box. But at least it'll tell you what you need. The big things you need are Yosis, Verilator. Oh, I didn't even talk about that. Talk about that in a second. Remind me to talk about testing. Open FPGA loader is the thing that gets it on the machine. The Apicula, I'm not really sure how to say that. That's just something needed by the build system. Next PNR, this is the place in routing stuff. You have to build this by source. Sorry. I mean, you basically, if you have next PNR, you have Yosis, and you have these other things, it'll just work. So this will kind of get you where you need to go. But real quick, I wanted to mention the testing part of it. It was actually super nice. Actually, the Game Boy one's probably the better one to look at.
You have 4 minutes.
There we go. We're going to use just regular Elixir testing. And so there's some tests up here, if you look at it, that are just saying, all these are going to be Verilator. Okay, well, the cool thing about the Verilator ones is, Verilator is essentially a simulator. So it's like Verilog simulator, I think is what it stands for. So this is actually going to like start running the machine with a certain clock cycle and literally like flip the clock, and you can write things into registers, read them out, assert on their values and stuff. So it's actually like these types of tests are normally written in C++. I took a stab at like actually writing a Zig library that does the same thing. And the Elixir one is surprisingly like way, way better. So like, this is the test for like, in Zig, right? So here's a test for the add for the ALU, right? And like, it's better than C++, but like, let me find the ALU here. So which one's it? So there's the APU. Well, yeah, that's audio processing. So we want the CPU ALU, there we go. So there's add. There, like, look how much easier that reads, right?
Macros for the win, man. Macros for the win.
And they run pretty fast. Like, let me what is it, test all? Oh, I'm in GB. I need to go into. Oh, I don't have the mize here. I have. Where's test all? It's just test. Test all was the other one. Some warnings, but yeah, I mean these things are actually like spinning through a Verilator outputting simulation data. So if you look, where are they at? Hardware sim, right? So each one of these is outputting these simulation files. Do I actually save them? I don't. I need to though. They're giant files, like because they're every single clock pulse and what happened in the state. If you think about it, like your 27 megahertz clock, most of the time nothing's happening. Like it's just the same thing. Like if you have a counter that counts every second in a 27 megahertz clock for literally like 27 million frames, nothing's happening. But anyway, yeah. So the fact that it ran 27 seconds is not great, but the fact that it ran that fast and not 27 minutes of just Windows starting up is great. Same thing with Hardwire. Hardwire itself has test all. Why is my no? Where's my test? Oh, which is my test list. Okay. I need to make that unique. I need to make that the same on all of them. But I guess I'm failing testing this. Yeah. But anyway, yeah, it's been great to be able to like run the actual simulator tests and see them. It actually test the hardware and have like hundreds and hundreds of tests. And Claude's pretty good at writing them. So I was actually pretty surprised. Like the fact that it works is great. I'm also baking into the web UI the ability to actually run the simulator. So this down here, this waveform thing, if you do simulate, it will actually say, well, do you want to how much do you want to do? And you say, so in this case, I did 100 ticks, which would be 100 ticks of a 60 megahertz clock. So basically, nothing's going to happen. But so like here's the the thing ticking up and down, or the clock here actually just stayed 0 the whole time. This clock did. There should be a sys clock that is not. Oh, it's not tracked on this one. But anyway, so nothing is going to happen on these unless you went out to 27 million or something. So there's a different version of this I have to use that like highly compresses all of the data so that you're not storing like 17 megabyte files. But anyway, that's all I got.
It's awesome.
Cool.
I never thought I saw the day where we're compiling Elixir to logic gates.
Yeah, and these boards, by the way, like they're pretty cheap. Like the one on here, this is the Pang Nano 20K. You get just the board for like $30. These little BXs. This is the ICE 40 chip on here. It's that like it's crazy. It's that little tiny chip in the middle is the FPGA. But yeah, this one I think now you can get for like $10. So you can play around with these pretty cheap. If you're ever gonna go buy one though, let me know before you do. I can recommend some that not to get because there's certain like the Zinc boards and like any of the Xilinx ones, they just don't have great open source support. But it's coming. Like people are slowly reverse engineering / fuzzing these things to figure it out. All right, cool guys.
Well, thank you. It's really cool to see all the things you built so you could build the thing.
Yeah.
That's a lot of ways.
See what I'm going to do with that. The whole point of this thing, actually, by the way, you're not recording me right now, right?
Yes.
Okay, let's turn the recording off first. I don't want to make any promises.